Okay, good morning, and we are ready to start. The usual confirmation. Can you guys see the screen? Ali or Junaid, can one of you confirm?
Yes, sir, we can see the screen.
Great, thank you. And thank you for showing up in the morning. So I will just recap what we did last time. Is we talked about the Poisson process. It's one of the very important processes in sciences and engineering. So recap of Poisson process. So a random process is a Poisson process when it is satisfying the following properties. So first of all, x of 0 is 0, starts with 0. There is no negative time. There is no negative time. Time is always positive. And x of t has independent increments. What that means is k x of t2 minus x of t1. This is one random variable. This is one random variable. X of t2 is one random variable minus x of t1 is another random variable. And when you take the subtraction of two random variables, you will get another random variable. So this is one random variable. And x of t2 plus tau minus x of t1 plus tau . This is also one random variable. So these two guys are going to be independent. Well, not quite. Maybe just a little bit. X of t3, t4 minus t3. Oops. T4 minus x of t3. This is another random variable. And for this, we are assuming that t4 is greater than t3 is greater than t2 is greater than equal to t1. ठीक है? So ये आपके पास random process है. X of t इधर टाइम चल रहा है. ये इस टाइम के ऊपर t1 के ऊपर कुछ वैल्यू है, t2 पे कुछ वैल्यू है, t3 पे कुछ वैल्यू है, t4 पे कुछ वैल्यू है. And then we have Poisson arrivals in between. Poisson arrivals in between. यहाँ दरम्यान में कहीं इवेंट आ जाते हैं. कभी इधर आ जाता है इवेंट, कभी इधर आ जाता है, कहीं रैंडम इवेंट्स आ जाते हैं. ठीक है. So इस तरह रैंडम इवेंट्स आ रहे हैं. So the total number of events that you will see until time t1 is x of t1. Okay. The total number of events that you will see between t1 and t2 is xt2 minus xt1. Okay. And what we are saying is, okay, the number of events that you see here and number of events that you see here, those two numbers are independent. And we had defined x of t as the number of events accumulated in duration t, in duration t. और ये नहीं हमने बताया कि ये duration कब है. ये 0 से t तक भी हो सकती है, ये 100 से 100 plus t तक भी हो सकती है. Okay. Duration t. So the duration is could be 0 to t or 75 to 75 plus t. कुछ भी हो सकती है, and so on and so forth. So x of t is, since it is counting the number of events, so this is a discrete alphabet process. Discrete alphabet process. And since this is counting the events until time t, so this is a continuous time process. Continuous time process. It has independent increments. It also has what we call stationary increments. Stationary increments. Stationary increments का क्या मतलब है कि x of t2 minus x of t1, the number of events that you will see between t2 and t1 is equal to, is the same as same distribution as x of t2 minus t1, as x of t2 minus t1. And also x of t2 minus t1, which is the same as, has the same distribution as x of t2 minus x of t1. This guy is Poisson lambda t2 minus t1, और lambda जो है उसको हम कहते हैं rate of the process. Rate of the process. Yeah. So very closely related to the Poisson random variable, except that it is indexed in time. So that means so the probability x of t is equal to k is equal to, it's a Poisson random variable, and taking a value of k with parameters lambda t power k over k factorial. So this is all our Poisson random process. ये सब कुछ Poisson random process. We talked about the waiting times and inter-arrival times. So if you have a Poisson random process, you have time here and events are arriving randomly. So let's say कि एक event यहाँ पे occur करता है, एक event जो है वो यहाँ पे occur करता है, फिर एक event यहाँ पे occur करता है, फिर एक event यहाँ occur करता है, and then another event occurs here. So the time starting from 0 until the first event occurs, it's T1. This T1 is called the inter-arrival time between 0 and the first arrival. So this is first arrival. And this is the second one. This is the third one, fourth one, and so on and so forth. The time until the next arrival is T2, T3, and then T4. Okay. And these T's are called inter-arrival times. कि जो events arrive कर रहे हैं Poisson distribution के through. The inter-arrival time means कि दो consecutive arrivals के बीच में जो time है, that's the inter-arrival time. And then we also had the waiting times. पहले के लिए जो waiting time है, it's W1. दूसरे के लिए जो waiting time है, it's W2. So you can see that there is a close relationship between W's and T's, W3. So Wn is really nothing but I is equal to 1 to n Ti. Waiting time for the nth event is inter-arrival time. पहले n events के आप वो add कर देंगे, and that would be your waiting time for the nth event. This is the waiting time for nth event, starting from 0. And then we showed कि inter-arrival times are exponential lambda. ये हमने कैसे शो किया था? ये हमने ऐसे शो किया था कि probability T1 greater than T, इसका क्या मतलब है? इसका मतलब है कि events are arriving here. यहाँ पे you have time. The events are arriving. The first arrival here, second arrival here, starting from 0. So this is T1. The probability that T1 exceeds certain time T, इसका क्या मतलब है? इसका मतलब है कि T टाइम के अंदर, स्मॉल T टाइम के अंदर कोई इवेंट अकर नहीं किया, क्योंकि पहले के लिए जो अराइवल टाइम है उसका स्मॉल t से बड़ा है. पहले इवेंट का अराइवल टाइम स्मॉल t से बड़ा है. इसका मतलब है कि स्मॉल t के अंदर कोई इवेंट अकर नहीं किया. What that means is the probability that x of t, which is counting the number of events until time t, is 0. But probability xt is equal to k is a Poisson random variable. It's a Poisson random variable. यही तो Poisson process बनता है. So यहाँ पे x of t is equal to k को 0 put कर दें. So you will get e to the power minus lambda t. What that means is probability t1 is less than equal to t would be equal to 1 minus e to the minus lambda t. Okay. But this is the CDF of exponential lambda. So we conclude that okay, t1 is actually exponential lambda. Similarly, we can show that t2, t3, these are all exponential. These are all exponential lambda. We can also show that these are independent. Notes में show किया गया. कैसे show किया? Conditional probability निकाल के. Okay. Now, since all of these are exponentials, so you can see that W's are just the summations of exponentials. And we have seen before, okay, if you add exponential random variables, if you have many independent exponential random variables, you add them together, you get a gamma distribution. So that means okay, the waiting times W i's are gamma random variables. Why? Because sums of independent exponentials. Independent exponentials का sum है, which we had shown long time ago, कि these are gamma random variables. The gamma random variables. So Wn, which is equal to summation I is equal to 1 to n ti. This leads to the conclusion that Wn has a distribution, gamma distribution with parameter n and lambda. See, exponentials को जब आप add करते हैं with all of them with the same rate, same parameter lambda, all of these independent, you get a gamma random variable. There is a way to prove that the distribution of Wn is gamma. हमने एक उसका एक छोटा proof show भी किया हुआ है. We had shown a similar kind of proof several lectures ago. So we are providing that in the notes. So summary. How do I summarize the Poisson random process? Summary of the Poisson random process. If x of t is Poisson random process with rate lambda, then the tn's are exponential lambda IID, independent identically distributed, and Wn's are gamma n comma lambda, So these are interarrival times and these are waiting times. Okay. So if you have multiple Poisson processes that are independent, you can merge them together. Merging independent Poisson processes. Okay. So I will give you a real world example. So suppose you are receiving tokens from one source. वो अब बस आपके पास जो है रैंडम टाइम्स के ऊपर अराइव होते हैं and those times are Poisson are waiting times are gamma distributed, interarrival times are exponential distributed, and the number of arrivals in a duration is governed by the Poisson random variable. तो एक जगह से आपके पास जो है वो टोकन्स आते जा रहे हैं. Let's say एक दूसरी जगह से आपके पास different tokens are एक जगह से red tokens आ रहे हैं, एक जगह से blue tokens आ रहे हैं, and all of these are being collected with you. So that means that you are merging these two independent Poisson process. So let's say this is you, and you are receiving black tokens as Poisson process. As Poisson process. What that means is, as Poisson process का मतलब ये है कि जो ये tokens आपके पास arrive होते हैं, ये black tokens arrive होते हैं. So these are arriving in a duration t. कितने tokens arrive होंगे? वो एक आपके पास Poisson random variable होगा. So now, let's say from another source, you are receiving red tokens. You are receiving red tokens also as Poisson process. Poisson process. And these two are independent. These two are independent. ये एक दूसरे से इंडिपेंडेंट है. ब्लैक वाले अलग एक सोर्स से आ रहे हैं, रेड वाले अलग सोर्स से आ रहे हैं. सो आपके पास यहाँ पे एक बकेट है और उसके अंदर आप you are collecting these red tokens and you are also collecting these black tokens. So total number of tokens जो आपके पास यहाँ जमा हो रहे हैं, we can show that it's the sum of, well, this is the sum of these tokens. You can show that this is also a Poisson process. This guy is also a Poisson process. And it's the merged or summed up Poisson process. So I will give you the definition. If x1t, x2t, etc., xmt, m sources से आ रहे हैं, except instead of two sources, you are getting tokens from m sources, are independent Poisson processes with rates lambda 1, lambda 2, ... up to lambda m. ठीक है, ये rates हैं. Then x, which is the sum of these total tokens आपके पास कितने आ रहे हैं, sum of these I is equal to 1 to m xi, okay, for all t in 0 to infinity. Then x, which is this guy, is a Poisson process with rate lambda 1 plus lambda 2 plus lambda 3 ... plus lambda m. And it's no surprise. एक जगह से आपके पास on the average 10 tokens per minute आ रहे हैं, दूसरी जगह से 5 tokens per minute आ रही हैं, तो total आपके पास 15 tokens per minute आ रहे होंगे. So this lambda is the number of events received in a duration of time on average. क्योंकि ये, remember, this is the average value of the Poisson random variable as well, expected value of Poisson random variable. So this is no surprise. ये तो हमें शायद वैसे ही पता होना चाहिए था. हाँ, ये जरूर है कि it is also a Poisson process, और दोनों को जब मर्ज करें तो Poisson आपके पास आता है. We have shown a similar kind of example in the case of random variables. Random variables के केस में हमने ये शो कर दिया था. Now, if you can merge the Poisson processes, you can split the Poisson processes as well. So splitting the Poisson process. So let's say you are receiving these tokens one after the other. ये आपके पास आते जाते हैं, ये tokens आ रहे हैं, and then randomly कुछ tokens को तो आप black रहने देती हैं, कुछ tokens को आप black रहने देते हैं, randomly choose करके कुछ tokens को आप red कर देते हैं. हमें नहीं पता किन tokens को red किया, किनको black किया, but for each token, for each received टोकन कह लें या पैकेट कह लें या चिप कह लें या कॉइन कह लें, जो भी चीज है, ये आपके पास एक बॉक्स आ रहा है, ठीक है. फॉर ईच रिसीव्ड टोकन, ये आपके पास जो अराइवल्स हो रही हैं, इफ दिस इज Poisson प्रोसेस विद सम रेट, ठीक है, देन वी कैन शो दैट कि अगर आप फॉर ईच रिसीव्ड टोकन इफ मार्क रेड with probability P and left black also with probability 1 minus P, ठीक है. So हर टोकन जो आपके पास रिसीव हो रहा है, आप देखते हैं उसको with probability P, एक आप उसको जो है वो रेड बना देते हैं, और with probability 1 minus P उसको ब्लैक का ब्लैक छोड़ देते हैं. Then if x of t t is Poisson process with rate lambda t, then यहां पर जो आपके पास x1t प्रोसेस मिल रहा है और x1t और ये इसको x2t कह देते हैं, ठीक है, x1t and x2t. So x1t is also Poisson process, with rate. Any guesses? इसका क्या रेट होगा? Any guesses? So ये आपके पास लैम्डा के रेट के ऊपर यहाँ पे पैकेट्स आते जा रहे हैं. विद प्रोबेबिलिटी p आप उनको रेड मार्क कर देते हैं, विद प्रोबेबिलिटी 1 माइनस p आप उनको ब्लैक मार्क कर देते हैं, ठीक है. सो x of t, this guy x of t is a Poisson process with rate lambda t. So I am interested in finding x1 of t. Claim is that this is also a Poisson process. ये हम proof भी कर सकते हैं, but I will skip the proof, लेकिन I will show the result कि क्या result क्या है. x1t will also be a Poisson process, लेकिन उसका रेट हम गैस कर सकते हैं. उसका रेट क्या होना चाहिए? देखें, with probability p आप मार्क कर रहे हैं x1 of t को, with probability p आप मार्क कर रहे हैं. So that means कि इसका रेट क्या होना चाहिए? कोई गैस लगाएं. Lambda t is the rate of this arrival process, and with probability p वो x1t बन जाता है, with probability 1 minus p वो x2t बन जाता है. So what would be the rate of x1t? x1t एक Poisson process होगा, उसका रेट क्या होना चाहिए? उसका रेट p होना चाहिए. Actually I shouldn't say कि rate lambda t, वो Poisson process है, lambda t का रेट उसका lambda है. So what would be the rate of x1t? So the rate would be, किसी ने कहा कि p होगा, नहीं p नहीं हो सकता क्योंकि फिर lambda कहाँ चला जाएगा. अब अगर ये इसका रेट p हो जाए और इसका रेट 1 माइनस p हो तो उस lambda बेचारे का तो कोई फर्क ही नहीं हुआ. हम ये कह रहे हैं कि फिर ये जो आपके आउटपुट के ऊपर रेड और ब्लैक है, ये आपके इनपुट वाले ब्लैक से जो है वो किसी तरह से डिफरेंट है. That's not the case, ठीक है. So this would be p times lambda, and x2t is also a Poisson process with rate 1 minus p lambda, rate 1 minus p lambda. So that the sum of these two rates, मैं इन रेड और ब्लैक को दोबारा से मर्ज कर दूं तो मेरे पास ये पुराना वाला आ जाना चाहिए, और उनको मर्ज कर दें तो वो देखिए मेरे पास रेट क्या आता है, lambda 1 plus lambda 2. So this would be p lambda plus 1 minus p lambda, which will be lambda, which is actually the case. This is actually the case. We can also talk about the Poisson process in the spatial domain. Okay. Remember when we defined the random process, we said that the random process is a indexed collection of random variable, and the index is usually time, but the index can be space as well. So we can also define what we call a spatial Poisson process. Space के अंदर एक Poisson process होता है, जिसके अंदर आपके पास, you have these Poisson distributed points, और ये यहाँ पे आपके पास कहीं पे एक origin है, and the distance from the origin to the nearest guy is t1, second nearest guy is t2, third nearest guy is t3, fourth nearest guy is t4, and so on and so forth. So we can show that this is also a Poisson process, but in this case there is no time. यहाँ पे आपके पास time नहीं है, सिर्फ आपके पास space है. And this is very useful for modeling defects on a chip. जब ये चिप मैन्युफैक्चर करते हैं उसके ऊपर जब डिफेक्ट्स आते हैं उनको Poisson रैंडम प्रोसेस से आप मॉडल कर सकते हैं. So now what are the mean and autocorrelation functions of the Poisson process? Mean and autocorrelation function of the Poisson process. We saw it last time. ये हमने last time देखे थे कि mean of Poisson process, mean and autocorrelation function of the Poisson process. We saw this last time कि mxt was equal to lambda t, and Rx T1 T2 was equal to lambda min T1 T2. ये हमने last time देखे. So what this tells us, the first equation tells us कि the mean is increasing with time. Mean is not constant. It's not constant. Which means it's not Whiteson stationary. Whiteson stationary नहीं हो सकता क्योंकि उसका तो mean ही constant नहीं है. ऑटो कोरिलेशन T1 माइनस T2 का फंक्शन वो तो हम बाद में देखेंगे. सबसे पहले तो मीन को कांस्टेंट करना है. इफ द मीन इज नॉट कांस्टेंट, द प्रोसेस इज नॉट Whiteson stationary. Process is not Whiteson stationary. Okay. Now, since this process is not Whiteson stationary, however, using the Poisson random variable, using the Poisson process, we can define additional processes which are Whiteson stationary. And one such process is called a random telegraph signal. Random telegraph signal. Very closely related with the Poisson process. So, आपको हम बता देते हैं ये क्या है ये random. This is a also discrete alphabet and continuous time. Discrete alphabet continuous time process. और बहुत ही सिंपल सा ये प्रोसेस है. Now, Poisson process tells you the count until time t or count in a duration t. Count of the events occurring in a duration t. 15 मिनट के अंदर बैंक में कितने कस्टमर्स आ गए, आधे घंटे में पीडीसी की लाइन में कितने कस्टमर्स आ गए, 1 घंटे में कितने पैकेट्स कंप्यूटर नेटवर्क पे अराइव हुए. So all of those are count of the events. Random telegraph is not the count of the events. However, it is dependent upon the count of the events. So x0 इसमें we take x0 to be equal to +1 or -1 with probability 1/2. Now, this random process can only take 2 values. या ये +1 ले सकता है या -1 ले सकता है. And you start with +1 or -1 randomly. एक कॉइन टॉस कर लिया, स्टार्ट कर देंगे या +1 से या -1 से. So एक सैंपल फंक्शन हम इसका ड्रॉ करते हैं. इसका. So you start with at t is equal to 0, time t is equal to 0. Time t is equal to 0. फिर स्टार्ट करते हैं. तो either you will have +1 or you will have -1. Let's say you have, सबसे पहले आपको ये +1 मिल जाता है. -1 से भी स्टार्ट कर सकते थे, लेकिन that would be another sample function. So I'm talking about just one sample function, and this remains constant. ये +1 पे ही रहता है. This remains constant until something happens. Until something happens here. ये T1 पे कुछ अकर करता है. जहां पे कुछ अकर करता है, जब पहला इवेंट हुआ, इसने फौरन से फ्लिप हो जाना है. फ्लिप होके ये -1 बन जाए, बन जाएगा. फिर ये -1 रहेगा. कब तक? Until something else happens. वहां पे जाके ये वापस फ्लिप होगा और फिर उसके बाद फिर कांस्टेंट रहेगा +1 के. So that means you can see it's just taking two values, +1 or -1, and it just flip-flops between +1 and -1 at these random times. ये इन टाइम्स के ऊपर जो है वो फ्लिप करता है. ये टाइम कहां से आएंगे? ये T1, T2 ... are waiting times to flip, and these are the waiting times derived from a Poisson process. So यूं समझ लें कि जो आपके पास Poisson arrivals हैं, वो आपके पास जो Poisson arrivals हो रही हैं, एक इस जगह अराइवल हुई, सेकंड अराइवल इधर हुई, थर्ड अराइवल इधर हुई. जहां पे अराइवल होती है, हमने काउंटिंग नहीं करनी है, हमने उस अराइवल को एज ए ट्रिगर यूज करना है टू फ्लिप द पोलैरिटी ऑफ दिस सिग्नल. So at times that are Poisson distributed, at time instants, times कह लें या time instants कह लें, at time instants that are Poisson distributed, the polarity is reversed, is flipped. So +1 से -1 हो जाता है या -1 से +1 हो जाता है. These are the, so you can see that this is very closely related with the Poisson process. We can show that random telegraph signal is wide sense stationary. This random telegraph signal is wide sense stationary. कैसे शो करते हैं? सबसे पहले तो what is probability x of t is equal to 0? ये भी हमने बताया कि what is the probability x of t is equal to 0 is +1/2, not 0. 0 तो ये हो नहीं सकता, is +1. Probability x of, sorry, this should be x of 0 is +1 and x of 0 is -1. This is also 1/2. So you start with either this point or this point. किसी एक जगह से start करेंगे, ठीक है? But we are interested in finding out what is the probability x of t is equal to +1. ये कैसे पता चलेगी? x of t is equal to, ये t is a time, ये कहीं पे भी हो सकता है, ये इस जगह पे हो सकता है, इस जगह पे टाइम है, इस जगह पे पोलैरिटी क्या है? वेल, ये अभी हमें पता नहीं पोलैरिटी क्या है, ये हमें पता नहीं. ये डिपेंड करता है कि कितनी दफा फ्लिप हुआ है, कहां से स्टार्ट हुआ था और कितनी दफा फ्लिप हुआ है. सो फर्स्ट वी नो कि the probability that x0 is +1 is 1/2. ये तो हमें गिवन है, ये तो हमें पता है, इस प्रोसेस का ये पार्ट है. सो द प्रोबेबिलिटी x of t is equal to +1, इसको हम लॉ ऑफ टोटल प्रोबेबिलिटी x of t is equal to +1 given x of 0 is 0 into the probability x of 0 is equal to 0. Sorry, ये 0 नहीं होगा, this would be -1 plus the probability x of t is +1 given x of 0 is +1 into the probability x of 0 is +1. So this is from the law of total probability. So we know these probabilities. X of 0 is -1, probability x of 0 is +1. This is 1/2, this is 1/2. What is this probability? Let's try to find out. ये क्या कह रही है? पहले जरा इसके बारे में सोचें कि probability x of t is equal to 1 given x of 0 is -1. इसका मतलब ये है कि आपने कहीं पे फ्लिप किया है 0 और t के बीच में, आपने कहीं पे फ्लिप किया है. You have 0 here and you have t here. ठीक है? 0 पे आपके पास ये -1 था, 0 पे आपके पास ये -1 था और t पे आके वो आपके पास ये +1 है. t पे आके +1 है और यहाँ -1 से स्टार्ट किया था. इसका मतलब है कि between 0 and t in this duration आपने एक दफा फ्लिप किया है, राइट? एवरीवन एग्रीज विद दैट कि यू हैव फ्लिप्ड एट लीस्ट, आपने एक दफा फ्लिप किया है या 3 बार फ्लिप किया है. 2 बार फ्लिप नहीं हो सकता, 2 बार फ्लिप करेंगे तो आप वापस -1 पे आ जाएंगे. सो between 0 and t you have made an odd number of flips आपने की. any question about that? कोई इसके बारे में कोई सवाल है? सो आपने स्टार्ट किया 0 के ऊपर -1 से, और हर दफा जब भी कोई इवेंट अकर करता है, जब भी कोई अराइवल होती है जो पोसॉन से आती है, you make a flip. -1 से +1 चले जाते हैं, +1 से -1 आ जाते हैं, ये जैसे हमने दिखाया यहाँ पे, you go from -1 to +1 और +1 to -1. okay? So हम ये कह रहे हैं कि 0 के ऊपर you had a value of -1, the random process had a value of +1 at t. मुझे इसकी प्रोबेबिलिटी निकालनी है. So इसका मतलब है कि मैंने दरमियान में जो फ्लिप किए हैं, we made an odd number of flips. Odd number of flips. So if nt is the underlying Poisson process, then probability x of t is equal to +1 given x of 0 is -1 is the same as saying that probability that n of t is an odd number. N of t is an odd number. Okay. So now I can write the expression for this guy. इसके लिए हम expression लिख सकते हैं. Probability x of t is equal to +1 is equal to this conditional probability into 1/2. So this would be 1/2 probability n of t is odd plus 1/2 probability n of t is even. N of t is even. But n of t is Poisson. N of t is Poisson lambda t. Is Poisson lambda t. So how can I make n of t to be even? The probability of n of t to be even or odd. So probability n of t is even. इसका मतलब यह है कि you add up all of those Poisson probability, j is equal to 0 to infinity. Lambda t power 2j. Lambda t power 2j e to the minus lambda t divided by 2j factorial. ये हमने क्यों 2j किया है? क्योंकि to make sure कि ये आपके पास even वाली values, even वाले terms को सिर्फ काउंट करें. Even वाली terms को सिर्फ काउंट करें. Similarly, probability that nt is odd is also j is equal to 0 to infinity lambda t power 2j plus 1 या 2j minus 1 जो भी लिख दें e to the minus lambda t divided by 2j factorial. 2j factorial. See? So that means now I can write the expression for x of t is equal to 1. We were trying to figure out कि एक फ्यूचर वाले टाइम में you started with a random time. आपने 0 से स्टार्ट किया with a random value, ये -1 से या +1 से स्टार्ट किया एक फ्यूचर किसी टाइम के अंदर. अब हमने देखना है कि जो रैंडम प्रोसेस था ये +1 था या -1 था. ये रैंडम टेलीग्राफ सिग्नल was this +1 or was this -1? And that is the probability xt is equal to +1 हम find out करने की कोशिश कर रहे हैं. ठीक है. So now if you recall, e to the power a plus e to the minus a divided by 2 was equal to 1/2. और e to the a की expansion क्या होती है अगर इसकी टेलर सीरीज expansion करें? So this is 1 plus a square over 2 factorial plus a cube over 3 factorial plus so on. Plus e to the minus a would be 1 minus a plus a square over 2 factorial minus a cube over 3 factorial plus so on. ये दो टेलर सीरीज मैंने ऐड कर दी. e to the a की एक टेलर सीरीज है और e to the minus a की एक टेलर सीरीज है. So this would really be equal to 1/2 into this guy. So ये 1 वाली जो टर्म है ये डबल हो जाएगी. So this would be 1 plus a square over 2 plus a 4/4 factorial plus so on. सिर्फ ये इसके अंदर ये इवन टर्म्स आ रही हैं. सिर्फ आपके पास इवन टर्म्स आ रही हैं. That means I can write using this expression I can write probability n of t is even is equal to ये देखें यहाँ पे आपके पास this is this guy here. This is lambda t 2j over 2j factorial. So ये आपके पास ये इस exponential type की चीज बन रही है, going j from 0 to infinity. So this is equal to e to the lambda t plus e to the minus lambda t divided by 2 multiplied by this guy, ये e to the minus lambda t, ये जो रह गए e to the minus lambda t. Similarly, probability nt is odd. इसकी probability क्या होगी? E to the minus lambda t minus e to the minus lambda t divided by 2 multiplied by e to the minus lambda t. Now we can go ahead and calculate the probability that x of t is 1. Probability x of t is plus 1. We can calculate this probability. It says 1 over 2, the probability nt is odd, plus 1 over 2, the probability nt is even. Okay, so this would be 1 over 2 into this guy here plus 1 over 2 into this guy here. तो इसमें से you will see कि ये terms आपकी जो हैं वो सारी cancel हो जाएंगी, ये terms सारी cancel हो जाएंगी. करके देखते हैं. So this would be equal to 1 over 4 1 minus e to the minus 2 lambda t plus 1 over 4 1 plus e to the minus 2 lambda t, and this would be equal to 1 over 4 plus 1 over 4 which is 1 over 2. Wow, ये किसी ने अगर रैंडम गैस भी करना होता ना तो वो यही गैस करता कि ये आपके पास एक रैंडम टेलीग्राफ सिग्नल है which started from somewhere, which started at t is equal to 0, या +1 से स्टार्ट हुआ था या -1 से स्टार्ट हुआ था. हमें कुछ पता नहीं है कहां से स्टार्ट हुआ था. इररिस्पेक्टिव जहां से भी स्टार्ट हुआ था, एट ए फ्यूचर टाइम आपने 100 साल के बाद इसको देखा. अब आपने ये देखना है कि रैंडम टेलीग्राफ सिग्नल की वैल्यू जो है आफ्टर 100 ईयर वो +1 है या -1 है, +1 है या -1 है. Does not matter whether you started from +1 or you started from -1. After 100 years or 200 years or million years, the probability that you will have this random telegraph signal taking a value +1, उसकी probability 1 over 2 है. Similarly, probability x of t taking a value of -1, सिर्फ दो ही values तो ले सकता है ये. So this would be 1 minus 1 over 2, which is 1 over 2. Now we can find the mean and autocorrelation function of random telegraph signal. ये बहुत आसान है. Now mxt is equal to +1 probability x of t is equal to +1, thus -1 into the probability x of t is equal to -1. And we just found out that this is +1 into 1 over 2 plus -1 into 1 over 2. So this is equal to 0. Zero mean. Let's try to find out the variance of xt as well and see if it is constant. Variance would be equal to expected value of x squared t minus expected value of x of t whole squared. ये तो वैसे ही 0 है. ये अभी हमने फाइंड आउट की है. Expected value of x of t 0 है. So what about this guy? Expected value of x squared t. So this would be equal to +1 squared into the probability it takes the value +1 plus -1 squared into the probability it takes the value -1. So this turns out to be 1. So variance of x of t is 1, which is constant. This looks like a Whiteson stationary process to me. It would actually be a Whiteson stationary process. Just to verify, इसकी autocorrelation function निकालते हैं, rxt1t2, which is expected value of xt1, xt2, xt1, xt2. Now xt1 और xt2 ये या +1 वैल्यू ले सकते हैं या -1 वैल्यू ले सकते हैं. ठीक है, या ये +1 वैल्यू ले सकते हैं या -1 वैल्यू ले सकते हैं. So they will either take same value, they will either take same value or they will take a different value. So चार ही possibilities हैं आपके पास ना. So this would be equal to +1 when they both take the same value. Probability x of t1 is equal to x of t2 when they both take the same value, plus -1 when they take the different values, x of t1 not equal to x of t2. So this is equal to, in fact, if we realize कि ये probability x of t1 is equal to x of t2, ये क्या चीज है? ये आपसे ये कह रहा है कि t1 और t2 के बीच में, even number of flips हुए हैं, even number of flips between t1 and t2, which means कि nt2 minus nt1 is even. Or since it has stationary increments, n of t2 minus t1 is even. Poisson process has stationary increments, so n of t2 minus t1 is even. And we go through this same process. कि इसकी probability even की और odd की probability कैसे निकालते हैं? We have already found that. लेकिन यहाँ पे अब ये साइन थोड़ा फ्लिप हो गया, तो अब जो टर्म्स यहाँ पे कैंसिल करनी थी हमने, ये वाली टर्म और ये वाली टर्म जो कैंसिल हो गई थी, अब ये कैंसिल नहीं होंगी, अब ये 1 और ये 1 कैंसिल हो जाएंगे क्योंकि यहाँ पे एक माइनस आ जाएगा. So you will end up getting Rx T1 T2, you will end up getting e to the minus 2 lambda T2 minus T1. It's a function of T2 minus T1 or T1 minus T2. So wide sense stationary. Mean will be constant था, तो ये wide sense stationary भी आपके पास है. So you can see that although Poisson random process itself was not wide sense stationary, we used the Poisson random process to generate a random telegraph signal. ये random telegraph signal ऐसा है कि वो process या +1 value लेता है या -1 value लेता है. You start with a random value, इनमें से +1 से या -1 इन दोनों में से किसी से start कर देंगे और specific times के ऊपर value को flip कर देंगे. और वो time कहाँ से आएंगे? वो time आएंगे जब वो Poisson process, जब आपका underlying Poisson process जब उसमें इवेंट अकर करेगा, जब इवेंट अकर करेगा. So this finishes our discussion for Poisson random process. It will come back later on when we talk about Markov chains, but for now we will hold on to that, and I will finish the discussion on the random processes. I'm going to talk about Gaussian random processes. GRP. So if you have a process x of t is a Gaussian random process if x of t1, x of t2, x of t3, so on. All of these, ठीक है. सब टाइम के ऊपर जो आपके पास T1, T2, T3 are jointly Gaussian. Jointly Gaussian का मतलब है कि एक वो specific form लेते हैं for the probability, joint probability density function. We have a couple of examples in the notes. I will do one example here, Gaussian random process. I will do one example. And this example is, let's say, a Gaussian random process. A Gaussian random process has mean mxt to be equal to 3t. Is this process stationary or no? Yes or no? Stationary or no? Wide sense stationary हो सकता है या नहीं हो सकता? Answers in the chat window. No, it cannot be constant because t के mean ही constant नहीं है तो वो wide sense stationary कहाँ से हो सकता है? So let's say कि you have cx Cx T1 T2. The autocovariance is 9 e to the minus 2 T1 minus T2. It's a function of T1 minus T2. अब स्टेशनरी हो सकता है, वाइट स्टेशनरी हो सकता है, यस और नो? आंसर्स इन द चैट विंडो. अब भी नहीं, क्योंकि मीन तो फिर भी जो है वो कांस्टेंट नहीं है. मीन तो फिर भी कांस्टेंट नहीं है. ये दोनों चीजें ट्रू होनी चाहिए फॉर द प्रोसेस टू बी वाइट स्टेशनरी. सो वी आर बीइंग आस्क्ड व्हाट इज द प्रोबेबिलिटी कि x of 3 is less than 6. X of 3 is less than 6. ये probability find करते हैं. Well, we know that x of 3 is a Gaussian random variable. Is a Gaussian random variable. Why it is a Gaussian random variable? Because हमें पता है कि xt is a Gaussian random process. अगर ये Gaussian random process है, तो x of t1, x of t2, x of t3, these are all jointly Gaussian for all t1, t2, t3, etc. ये सब Gaussian होने चाहिए. इसका मतलब है इंडिविजुअल भी Gaussian होने चाहिए. ये नहीं हो सकता कि दो चीजें इंडिविजुअली Gaussian ना हो और jointly Gaussian हो. वो इंडिविजुअली भी Gaussian होंगी, which means कि x of 3 is a Gaussian random variable. हमने ये probability find out करनी है. I can easily find out this probability if I know the mean and variance of x of 3. So need mean and variance of x3. Need mean and variance of x3. इसकी mean और variance चाहिए. How do I find the mean of x3? इसका mean क्या होगा? Expected value of x of 3 would be equal to mx3, which is equal to 3 times 3, which is 9. Right? What would be the variance? What would be the variance? Variance कैसे निकालेंगे? We are given the covariance function. We are given the covariance function. So the variance of x3 is simply cx 3, 3, which is equal to 9 e to the minus 2 into 0, which is equal to 9. ये 9 आता है. Which means कि x of 3 जो है वो आपके पास एक normal random variable आ गया, which means 9 and variance also 9. Now I can answer this question कि probability x of 3 is less than 6 is equal to कि probability your कैसे मालूम करेंगे? Any ideas? How do I find this probability? Answers in the chat window. स्टैंडर्ड नॉर्मल में कन्वर्ट कर लेते हैं. स्टैंडर्ड नॉर्मल में कैसे कन्वर्ट करेंगे? स्टैंडर्ड नॉर्मल में ऐसे कन्वर्ट करेंगे, लेस देन 6 minus 9 over square root of 9. 6 minus 9 and this turns out to be 0.16. ये स्टैंडर्ड नॉर्मल के टेबल से देख लेंगे इसको. सो आपके पास क्या आंसर आ गया? सो वेरी वेरी इंटरेस्टिंग, वेरी वेरी इजी. कोई इशू ही नहीं है गॉसियन रैंडम प्रोसेस के अंदर. I am going to talk about another process which is derived from the Gaussian random process. It's called Gauss-Markov process. Gauss-Markov process. Gauss-Markov process. This is a process which is a Gaussian random process, and it is also a process with Markov property. It's a Markov process, which means that given the present, the past and future, they will be independent. Given the present, past and future will be independent. Gauss-Markov process is also an example of first order autoregressive process. First order autoregressive processes होते हैं. We may not have time to go into the full detail of first order autoregressive process, but Gauss-Markov process is an example of one of those processes. कैसे define करते हैं इसको? So ऐसे define करेंगे x1 x2 डिफाइन करते हैं पहले इसको, x1 x2 डॉट 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 are IID normal 0 and variance n, normal 0 and variance n. So we define a process y1 to be equal to x1, y1 to be equal to x1, and y2 to be equal to alpha, some constant times y1 plus x2. Similarly, yn would be equal to alpha times yn minus 1 plus xn. So हर बार आप एक नया x ऐड करते जा रहे हैं, which are IID normal, और कुछ थोड़ी सी हिस्ट्री उसके अंदर डाल देंगे. These processes are Gaussian random processes as well as Markov random processes for every value of alpha. So this is Gaussian random process, also Markov property, also has the Markov, it's a Markov random process, the Markov property. Is this independent increment? Well, it is not independent increment. It is not independent increment. Is it independent increment? Not unless alpha is equal to 1. अगर अल्फा 1 हो जाए तो फिर ये इंडिपेंडेंट इंक्रीमेंट भी बन जाता है. गॉसियन तो रहता ही रहता है, मार्कोव भी रहता है. If it is the case that alpha is equal to 1, then this additionally becomes an independent increment process. Okay? For alpha is equal to 1, this is called a discrete time Wiener process. Discrete time Wiener process. Discrete time Wiener process. So let me try to find out the mean and autocorrelation function. Mean and autocorrelation function of Gauss-Markov process. Mean and autocorrelation function of the Gauss-Markov process. So we know, okay, y1 is equal to x1, which has a normal 0n. And we also know that yn is equal to alpha times yn minus 1, पूरी उसकी history multiplied by alpha plus xn. N is greater than 1, alpha is less than 1. Alpha is less than 1. And xi's are IID normal 0n. Normal 0n. So पहले मीन फाइंड करते हैं. सबसे पहले मीन फाइंड करते हैं इसका मीन. myn myn. By the way, is this a discrete time process or a continuous time process? This would be a discrete time process. This would be a discrete time process. Continuous alphabet or discrete alphabet? Well, since this is drawing from a normal distribution, so it has to be continuous alphabet. Would be continuous alphabet. Okay. So myn is equal to expected value of yn, simply expected value of alpha yn minus 1 plus xn. Expectation is linear. So this would be equal to alpha times expected value of yn minus 1. और x of n की जो expected value है वो 0 है. Expected value of xn is 0. Why? Because normal 0n है. Because it's a normal 0n. So you can see that this is a sort of a recursive equation. Okay? So expected value of yn हम find out कर रहे थे. Expected value of yn. This turned out to be in terms of expected value of yn minus 1. तो साथ एक alpha multiply हो रहा है. So I can continue this and write as expected value of yn minus 2 plus alpha cube expected value of yn minus 3, and so on and so forth. is equal to alpha n minus 1 expected value of y1. Which is equal to alpha n minus 1 expected value of what is y1? Y1 is the same as x1. x1, which is 0. So ये तो 0 ही आ गया. Okay, so the mean of the Gauss-Markov process is 0. Let's find the autocorrelation function. We use a trick for this, Ry and m. Okay, so assume m is greater than n. Assume m is greater than n. बाद में हम ये m smaller than n के लिए भी कर लेंगे. लेकिन Ry and m would be equal to expected value of yn ym, which is equal to the expected value of yn multiplied by alpha ym minus 1 plus xm. इनमें से सिर्फ एक को जो है मैंने उसकी यहाँ पे वैल्यू पुट कर दी है, जो डेफिनेशन है Gauss-Markov random process की. So let me just open this up a little bit. So this would be equal to expected value of yn xm, and there is a reason कि मैंने ये ym वाला जो है इसको ये एक्सपेंड किया है, yn वाले को नहीं एक्सपेंड किया, and you will see the reason. अभी आपको रीजन पता चलेगी. So this would be plus alpha times expected value of yn ym minus 1. ठीक हो गया ये? Now this guy yn and xm, they are independent. Why? Because m is greater than n, तो yn जो होता है उसमें उसकी अपनी पूरी हिस्ट्री आती है और xn आ जाता है. yn के अंदर उसकी एक पूरी हिस्ट्री आती है और एक नया xn आ जाता है. तो yn is dependent upon xn, लेकिन फ्यूचर वाले जो x's हैं उसके ऊपर डिपेंडेंट नहीं है. एंड सिंस m is greater than n, so xm जो है ये फ्यूचर वाला x है. ये एक फ्यूचर वाला x है जो बाद में ऐड होगा, किसी ym के अंदर ऐड होगा जाके, लेकिन सिंस n is smaller than m, so these two guys are independent. So these two guys are independent. This is equal to expected value of xm. ऐसे लिख सकते हैं इसको, independent है तो लिख सकते हैं. And this guy is 0. So that means I can write this as alpha times expected value of yn ym minus 1. This is your autocorrelation function. Okay. Expected value of yn ym. ये तो अभी आंसर आया नहीं, but this looks a recursive form to me. I can write it as alpha square expected value of yn ym minus 2 equal to alpha cube expected value of yn ym minus 3 and so on. कहां तक जाने? जहां तक ये m minus 1 2 3 ये m तक नहीं पहुंच जाते, जहां तक ये m तक नहीं पहुंच जाते. So that means I can write it as expected value of yn ym to be equal to, ये देखें अल्फा की जो पावर है वो ही यहां से माइनस हो रही होती है. ठीक है, so this would be alpha power m minus n expected value of yn, और y m में से इसको माइनस कर दें m minus n को, so you are left with yn. अब इसके ऊपर हम वो ट्रिक नहीं लगा सकते क्योंकि अब नाउ यहां पर तो m जो है वो n से बड़ा था, वो ट्रिक अब यहां पर नहीं लग सकती. But this we know is alpha power m minus n rynn. So let's try to find rynn. rynn निकालते हैं, which is the variance here, is equal to expected value of alpha by n minus 1 history plus the new value multiplied by the same guy. multiplied by alpha yn minus 1 plus xn। तो ये आपके पास जो है वो चार टर्म्स आ जाएंगी, ये आपके पास चार टर्म्स आ जाएंगी। दो टर्म्स ऐसी होंगी जिसके अंदर xn और yn माइनस xn का स्क्वायर वाली होगी, yn वाली होगी। I will write those terms here. So this would be equal to alpha square expected value of yn minus 1 ठीक है, एक ये वाली टर्म आएगी प्लस एक्सपेक्टेड वैल्यू ऑफ एक्स एन स्क्वायर, एक ये वाली आएगी, और फिर क्रॉस टर्म्स आएंगी अल्फा वाई एन माइनस 1 की एक्स एन के साथ, और फिर एक और अल्फा वाई एन माइनस 1 की एक्स एन के साथ। एंड सिंस दीज वुड बी इंडिपेंडेंट, सो एक्सपेक्टेड वैल्यू ऑफ एक्स एन आएगी प्लस 0, वो सब 0 आ जाएगा, सब 0 निकल आएगा। What is expected value of xn square? This is n. Why? Because xn is normal 0n. So this is simply variance plus the mean का square, or mean is 0. So this would be n. So ये आपके पास क्या बना? Alpha square. This is ry n minus 1 plus n. And what is this? ry n comma n. Oh, ये तो फिर recursive बन गई. This is recursive again. So I can write this as ry and n to be equal to, अब इसकी जगह पे हम लिखेंगे तो एक और आपके पास ये alpha square के साथ you will get alpha square ry n minus 2 comma n minus 2 n minus 2 plus n, और ये पुराने वाला n उसी तरह से आ जाएगा। So this would be equal to this will be turn out to be equal to, देखें आपके पास ये eventually you will have alpha 4 and then alpha 6, then alpha, so on and so forth. इसको थोड़ा simplify करें, so you will get 1 plus alpha square plus alpha 4 plus so on all the way up to alpha power 2 n minus 1. This guy multiplied by n. इतने सारे आपके पास n जमा हो जाएंगे। ये n1 के साथ मल्टीप्लाई हो रहा है, ये वाला n जो है अल्फा स्क्वायर से हो रहा है, एक और n आएगा वो अल्फा 4 के साथ होगा, एंड सो ऑन एंड सो फोर्थ until you will reach ry11 आपके पास जो है वो variance of ry11 would be the variance which would be another n. ठीक है? So you can see that this is a geometric series. This is a finite geometric series, and this should simply be equal to 1 minus alpha power 2n. कितनी टर्म्स हैं इसके अंदर? 1 पावर 0 है, so 0 से n minus 1, 0 से n minus 1, so there are n minus 1 terms here. There are n minus 1 terms here. 1 plus alpha square 2n, 1 minus alpha square. Geometric sum, geometric series है जिसका सम हमने ये किया times n. तो ये तो अभी ry n निकली है, लेकिन expected value of yn ym जो थी, जो आपके पास which was ry m थी, so ry m would be equal to ये alpha power m minus n से multiply होगा, would be equal to alpha power m minus n into 1 minus alpha power 2n over 1 minus alpha square. This is for m greater than n. If m is greater than n. m अगर smaller हो जाएगा तो ये n की जगह पे m आ जाएगा, m की जगह पे n आ जाएगा. In general, ry n comma m would be equal to alpha power, we can write it as m minus n, irrespective m बड़ा हो या छोटा हो, doesn't matter, m minus n लिख सकते हैं, and 1 minus alpha power 2, यहाँ पे ये n है, when n is smaller than m, अगर m smaller than n हो तो इसको मैं 2 min of n comma m कर सकते हैं, divided by 1 minus alpha square times n. Now somebody should tell me, is this process, Gauss Markov process, ये wide sense stationary है या नहीं है? Mean is constant 0 and autocorrelation function is this. Wide sense stationary or not? Yes or no? Answers in the chat window. नहीं है, क्योंकि ये this is not a function of m minus n. ये एक जगह पे तो आ रहा है लेकिन ये दूसरी जगह नहीं आ रहा, so m minus n को if I put m is equal to n, I am not going to get, I will still be left with m and n here, m or n here. So there is another example of first order autoregressive process, which will be given in the notes जो मैं upload कर दूंगा, and we will take a look at that. So I am going to very quickly talk about what we call the discrete time Wiener process. Discrete time Wiener process को define ऐसे करते हैं कि let xn be a discrete time wide Gaussian noise process. It's a Gaussian process, Gaussian random process. इसको मैं ऐसे लिख देता हूँ, discrete time Gaussian random process. Xn is normal 0, 1 IID. In fact, you can just forget about this. So xn 0 normal 0, 1 सारे standard normal for each value of n is equal to 1, 2, 3, 4, 5 and so on and so forth. Okay, so n is equal to 0, 1. ठीक है, so define करते हैं discrete time Wiener process को. कैसे define करेंगे? Define ऐसे करते हैं W0 is 0, you start with 0, very simple. Okay, and then Wn is just the summation I is equal to 1 to n, जैसे हमारा random walk में होता था, लेकिन random walk में you either go +1 or you go -1. Discrete time Wiener process में वो +1 और -1 नहीं होता, +1 -1 के बजाय आप एक normal को add करते हैं और subtract करते हैं. So this is this, that is steps are normal 0, 1 IID. Steps are normal 0, 1 IID. Since this is a random walk process in which the increments instead of +1 -1 they are governed by a random variable, but that doesn't take away the independent increment property. Okay, so this has independent increments just like the random walk had. So it has independent increments. इसके पास independent. And random walk was a Markov process. So Markov process as well. ये Markov भी होता है. ये process Markov process भी. So we can write Wn to be equal to Wn minus 1 plus xn. ठीक है. So ये देखें, ये बिल्कुल Gauss Markov process की तरह लग रहा है. वहां पे हमारे पास यहाँ पे एक अल्फा होता था. So I have made this alpha to be equal to 1. Alpha को 1 किया तो ये आपके पास discrete time Wiener process बन गया. So using the same procedure that we found for the Gauss Markov process जो अभी हमने discuss किया है. So you can find the mean of this. MWN is equal to expected value of WN, and this will turn out to be 0. And RWNM, which is expected value of WN, WM, Go through that recursive process again. Go through that recursive process again, and you will find that this is equal to n if m is greater than n. Okay. So Rw n comma m, this would be equal to min of n comma m. ये पहले भी हमने देखी है, रैंडम वॉक के केस में भी देखी है. No worries with that. And the variance of Wn is equal to, this will also turn out to be equal to n. ये हम निकाल सकते हैं. So this is the example of a discrete time Wiener process. The real Wiener process has continuous time. Is also a Gaussian random process. Is real Wiener process को, if you guys have heard about Brownian motion. So Brownian motion is modeled by the real Wiener process. Real Wiener process की definition क्या है? Real Wiener process की definition ये है, you again start with 0, okay? And then you have independent increments, बिल्कुल उसी तरह से जैसे random walk में होती है, which means that this is a Markov process as well. Okay? And then the third property is that Wt instead of n is normal 0, alpha t. अगर t आपके पास इंटीजर होगा, तो ये डिस्क्रीट टाइम वीनर प्रोसेस बन जाएगा. Once again, the mean of Wt is 0. The mean expected value of Wt is 0, and sigma square of W as a function of time is alpha t. Yeah. And autocorrelation or W T1 T2 will be equal to alpha times min of T1 T2. बिल्कुल उसी तरह से जैसे हमने ये पहले कंप्यूट किया था. And once again, real Wiener process जो है वो भी हम random walk की in the limit देख सकते हैं, in the limit. So random walk में अगर आप steps बहुत छोटे-छोटे कर दें, so random walk में थोड़ी टाइम के बाद you take +1 or -1. So instead of taking +1 -1 ये normal increments हो और time step भी बहुत छोटा हो जाए उसके अंदर, approaching 0, then the random walk will become the real Wiener process. और फिर random walk की जितनी भी properties हैं वो इसके ऊपर भी apply होती हैं. So this finishes our discussion for random processes. Well, not quite. We are going to start with Markov chains in the next class. Markov chains are special kind of random processes. And we will have a discussion of Markov chains on Wednesday in the next class. If there are any questions about these random processes, by the way, there is a lot more in the random processes domain that we have not been able to cover. You can do processing of the random process. You can pass these random processes through a filter. एक filter से इसको pass कर सकते हैं, and then you can talk about the properties. You can talk about the power spectral density of these random processes, and we have not covered that. This autocorrelation function, there is a very remarkable theorem which relates the power spectral density of a random process with the autocorrelation function through a Fourier transform. So we have not been able to talk about that. Leaving that for some other course. We will however cover the Markov chain and queuing theory starting from the next class. So next few lectures that we have remaining in the semester, we will be covering Markov chains, and time permitting, we might have one lecture on regression and machine learning. Okay. If there are any questions, we'll be happy to answer before we close the session. कोई question है? No questions. So I'm going to stop the share here and then close the session. Thank you very much. The video will be uploaded when it becomes available. Sometimes they make it available soon. Sometimes they take a while before it is available. Thank you for showing up in the morning.